Hello, so this is part 2 about linearization, and we're going to finish off this chapter, especially everything that is related to the textbook. And in the future videos, I may make a few more videos about logarithms, especially trying to solve questions from Cambridge or from the questions that I used to receive when I was in grade 11 in Bhutan. So that is my plan for now, but I'm not sure on how successful I will be at executing it. So this is basically asking you to prove that ln y against ln x is a straight line. But when I tried, I don't think it is a straight line. And when you refer the answer given in your textbook, it does not ask you ln y against ln x. It asks you y against x is a straight line. And if you solve this question, then your answer matches the one that the textbook expects you to give. So ln y against ln x, when I tried it, it is not a linear relationship between them. So let's say 5 2y is equal to 3 2x plus 1. And we can take the natural log of both sides. This gives us ln 5 to the power 2y, ln 3 to the power 2x plus 1. So 2y ln 5 is going to be 2x plus 1 ln 3. 2y ln 5 is going to be 2 ln 3 x plus ln 3. And finally, y is going to be 2 ln 3 over 2 ln x, x plus ln 3 over 2 ln x. And the 2's will cancel out, giving us y is equal to ln 3 over ln 5x plus ln 3 over 2 ln 5. And this is just your y, this is your x, this is your m, and this is your c. And you can see that this is a linear relationship. So now, your exact value of your gradient is ln 3 over ln 5. That is what the question asks you to give, and it asks you to give the exact coordinates of where the graph cuts the y-axis. So if you want to know where the graph cuts the y-axis, which is the y-intercept, you just put x is equal to 0. And when x is equal to 0, this whole thing cancels out, so you just have ln 3 over 2 ln 5. That is your y-intercept, that is c. So that is your answer for question 6. And now we have question 7. So the temperature of a hot drink is, after it is made, can be modeled by the equation. So basically you have a hot drink, maybe you're a cup of coffee or a cup of tea, and you're putting it in your room. Now usually your room is colder than your hot coffee. So your hot coffee is going to cool, and because there is a temperature difference, this relates to physics. So it's going to cool, and eventually it's going to reach thermal equilibrium, which is when the temperature of your coffee is equal to the temperature of your room. And that is where no heat exchange. There is no net exchange of heat between the cup of coffee and the environment. So basically, it asks you to convert the equation, this equation, to a suitable form for drawing a straight line graph. So t is equal to 25 plus ke to the power negative nt. Now, if you directly take the natural log of both sides, you get 25 plus e to the power negative nt. And this is not easy to work with because we don't have a rule that allows us to easily simplify this. So instead, we'll take 25 minus 25. We'll subtract 25 from both sides, ent. Now, if I take the natural log of this side, that is something that I can solve. So now, if I take the natural log, then I get ln ke to the power negative nt. So ln t minus 25 is equal to ln k plus ln e to the power negative nt. Ln t minus 25 is equal to ln k plus negative nt, right? Because ln e is just 1, and you can bring negative 1. And plus minus is just going to give you minus. So minus nt. And if you think about it, this is linear. This is your y. T is going to be your x-axis. This is your gradient. You have a negative gradient. And this is your y-intercept. So you have, this is the equation. So I'm not going to draw the graph because that is a bit difficult for me to draw it on my iPad. But you can draw on your graph. You can use a graph paper that will help you to estimate the value better. But we'll directly go to C. So estimate the initial temperature of your drink. So we will use this equation, the equation that we just found. T minus 25 is equal to ln k minus nt. And it says, hey, what is the initial temperature of the drink? Well, at t is equal to 0. So initial basically means when you start measuring, right? So I want to put my time, the small t, to be 0, and the temperature, whatever temperature that is going to be my T naught, my initial temperature. So ln T naught minus 25 is going to be ln K minus, if I put T 0, that's just going to be ln K. And basically, I'm going to get, so I think when you plot the graph, right, you're going to get the values of your K and your minus NT. But let me see if I can sort of get estimates from the table. And I think I can. So I know that, so before I start with this, I will have to figure out what my ln K is and what my negative n or my n is. So n I can solve very easily. N is just, this is, if I say this is y2 and this is y1 on the t-axis. So I need actually, so I can't use data from this. So if you plot the graph, this question is going to be a bit easier, but I haven't plotted the graph. So basically on my graph, on my y-axis, I have ln t minus 25. And on my x-axis, I have t. So I don't have to worry about t, but I need to convert. So let me just take two data points, these two, and my t does not change. So it's going to be 10 and 8, but I need to convert. So I need to put my t values into this equation. So ln 45.2 minus 25 is 3.00. So this is 3.005682604. And when it's at 8, t is equal to 8, ln of 48.7 minus 25 is, so this is a bit higher. So this is 3.16547575048. 75048. So I have at t is equal to 8, it's bigger. At t is equal to 10, I think it's smaller. 45.2, yes. Because it's cooling, right? So it's going to be decreasing. And now I can calculate m. So m is basically y2 minus y1. So let me take this to be my y2 and this to be my y1. So if I do y2 minus y1, and you can do it on your calculator, I get negative 0.159792444. And x2 is 10, x1 is 1, so 8. If I 10 minus 8 is going to give me 2, and my overall answer for my gradient is going to be negative 0.079896222. So that is my m. I'm sorry about that. Where did my answer go? Wow. So, okay, let me just write it again. So that is negative 0.079, So that is my m. And it's negative because it's decreasing. And that is something that we expected. So now, when I substitute my m into the equation, well, my relationship tells me that, hey, it's negative nt plus ln k. So negative n is my gradient, right? So my gradient is actually negative n. So my n value, gradient is negative n. So my n value is going to be, my n value is positive 0.07989 0.07989 So this is my gradient, and or my n value. My gradient is negative of that. And now I can use this to estimate my k value. So let me just take one data point. Say t is equal to 57.7. 57.7 minus 25 has to equal to negative 0.079 minus n. 896,222 times what temperature? So my T is at 4, right? 57.7 at 4. And what is the units? I have to be very careful here. Okay, T minutes. So it's related to minutes plus ln K. So I can calculate K using this equation. So ln, and this you won't experience this issue if you actually plot it out, because you can use your graph to estimate all of these. But I'm not drawing my graph, so I'm going to do everything manually. So ln 57.7 minus 25 plus 0.07989622 times 4. That is ln K. So ln K is about 3.8069599966, and therefore K is going to be e to the power of my answer. That is 45.0133. So 45.0 to 3 significant figures. And my n is going to be 0.08 to 1 significant figure. So let me just confirm. This is exactly how the textbook has. So yeah, they estimated n to 0.08 and they estimated k to be 45. So these are exact values. So these are more accurate values, but they have estimated this to 1 sig fig and this to 3 sig figs. So 45.0. So to get k, I just raise e to the power both sides. So now that I have n and k, so I didn't draw a straight line graph, so I estimated it using the data that I have, which is also something that you can do. So now I need to estimate the initial temperature of the drink. So I know that, hey, if I take, now I have this equation that we previously derived. So I know that T naught minus 25 is just K. So T naught is just K plus 25. So 45 plus 25, that gives me 70 degrees Celsius. So just take ln, exponentiate both sides to e, and then you get T naught minus 25 is K, and T naught has to be K, which is 45 plus 25 gives me 70 degrees Celsius. Now, let's take the time taken for the temperature to reach 28. So now let me just use my equation, my ln equation. So my ln equation tells me that, hey, ln T minus 25 is equal to ln K minus nt. And I know n, I know ln K, so I can just solve it. So I need to calculate T when my capital temperature is 28. So ln 28 minus 25 is going to be equal to ln K, and I know ln K. Ln K is this value, right? If you think about it. So ln K is just 3.8069599966 minus, I know n, which is this value, 0.07989622 T. And now finally ln, when I calculate 28 minus 25 and I subtract 3.8069599966 and I divide by negative 0.07989622, then I get my T to be 33.89. So I'll round it to 2 significant figures, that is 34 minutes. Now, usually during calculations, I'm not sure what your teacher will suggest you to keep the number of significant figures to, but if you look here, your T has been given to 1 significant figures, and your capital T, the temperature, has been given to 3 significant figures. So usually we want to keep it to, say, the lower significant figure, so it would have been 2, but then the textbook sort of awkwardly rounds it to, there's no consistent way, so I'm just rounding it to the next whole number. So I'm not leaving decimal points here, and if there are decimal points, I'm rounding it to 1 significant figure. So 34 minutes. And now finally, I need to calculate the room temperature. So now, how do we calculate the room temperature? Well, actually, it's obvious what the room temperature is. But basically, we want to put a very, very, very huge T to calculate the room temperature. So let me just show you. I have ln T minus 25 is equal to, well, let me just copy this equation. Let me just copy. Okay, so I have this equation, except instead of so instead of 28, I'm just going to say this is my TR, my room temperature. And to solve for room temperature, basically the idea is that if you allow your cup of coffee to cool and cool and cool, right? So basically, after a certain amount of time, it's not going to freeze. Your cup of coffee will not freeze. What will happen is that it will attain room temperature. And then there is no net exchange of heat. So it will attain, once it attains the same temperature as its environment, then it stops cooling. So basically, you want to put a very, 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 very huge T and see what happens. So ln TR minus 25, so if you solve this, well, you see that 3.80. So if I put, like, say, 10 to the power 30 minutes, 0.07989622 times, say, 10 to the power 30 minutes. That is a huge number of minutes. And I want to calculate 3.80, then now I put T is equal to 10 to the power 30 here. Because if I let it rest for a very, very long time, then my cup of coffee, using the laws of physics, is going to attain room temperature. So now, if I put a very, very huge T, then what happens is, and if I solve the question, if I try to solve the equation, so 3.80 minus this huge number is going to be a very, very huge negative number. So I'm going to get negative 7.9896222 times 10 to the power 28. This very, very negative number. And if I raise my e to this huge negative number, then it's effectively, if I raise both sides to e, then this side is basically 0. If you can use your calculator to verify, and I get my room temperature to be 25 degrees Celsius. And that is one way to look at it. And another way that is more direct, and I hope I can erase everything here. So another way to look at it that is more direct is that, let me just look at my initial equation. T is equal to 25 plus k to the power e negative nt. And this uses the same idea, except this relates to, if I simplify this, e 25 plus k divided by e to the power nt. And I think of what happens if my time tends to infinity. So this again relates to the concept of limits that we'll discuss. But if my t is very, 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 very big, this term is going to be 0 because my numerator is constant, k is constant. My numerator gets bigger and bigger and bigger. Exponential function is an increasing function, and it increases, exponentially. That's the name of the function, right? So it becomes very, 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 very big. And then the second term collapses to 0. So you get your room temperature, where thermal equilibrium occurs, to be 25 degrees Celsius. And that is it. That is the room temperature. And that is how you do question 8. So I know it took me a bit more time compared to what you would have taken if you just drew the graph, but I don't really have. It's very difficult for me to plot like 63.3 on scale on this iPad using the grid I have here. So please feel free to try to use your own graph paper and then solve it. And I think you will also be able to get the same answer. But this is how you do question 8. And that is, I believe, the end of the first chapter. And thank you very much. And we'll hopefully cover more videos on how to solve these. But that is it for this chapter.